Hi dear students, we discuss the next topic, that is Biot-Savart Law. You have already learned this topic in the plus 2 class. However, I just recall the Biot-Savart Law here. That is, if this is a current carrying conductor through which a steady current I is flowing, L is the total length of the wire, and in which I consider a small length segment, that is dl. The Biot-Savart law is used to find out the magnetic field at a distance r from this current carrying wire. Let me put that this is a point P. We will find the magnetic field at this point P because of the small length of the current carrying segment dl. That magnetic field is dB. That we need to find out. After finding out this small magnetic field due to this small length element, we will integrate that expression. Then we will get the total magnetic field produced by this wall length of the wire. Fine. The r cap is the distance vector to that point P, and here the angle between this distance vector and the small length element is theta. Okay, there is this dl sin theta, that can be written as dl sin theta can be written as dl cross r cap. Find this dB can be written as dB is equal to mu 0 by 4 pi I dl cross r cap divided by r square. Here this I is a constant one. This is a steady current. Its value is constant. Then I can write this dB as dB is equal to mu 0 I by 4 pi dl cross r cap by r square. And to find out the magnetic field to the whole length of the wire, I integrate this equation. That is, we can write the B is equal to line integral dB, that is equal to line integral. We can take the mu 0 I by 4 pi outside, dl cross r cap by r square. Okay, that is, this magnetic field B, this is the Biot-Savart law that gives the magnitude of the magnetic, that gives the value of the magnetic field at a distance r from the wire, where this mu 0 is equal to 4 pi into 10 power minus 7 Newton meter by ampere square. Fine. Now let us do a problem in the Griffith textbook. Question is this one. That is, find the magnetic field at a distance s from a long straight wire carrying a steady current I. Fine. I will draw the picture here. This is a wire that carries a current I and whose total length is L. We consider a small segment of the wire, that is length dl, and from this segment of the wire at a distance r, that is at the point P, we need to find out the magnetic field B. That is, we need to find out the magnetic field to the whole length of this wire at this distance s from this wire. For this, first we find out a magnetic field due to this small length of the wire at the point P. Then we will integrate the equation. The magnetic field at the point P due to the small length of the wire is dB. Fine. Here the angle between this distance S and this distance R, that is this is equal to, this is theta. The distance between the small length element dl and this R, that is this angle, that is nothing but phi. Magnetic field at a distance R due to the small length of the wire is given by dB is equal to mu 0 I by 4 pi in dl cross r cap divided by r square. Fine. Here the dl cross r, that is equal to dl its magnitude, r cap its magnitude, sine phi, because if you look at it, if you look at this picture here, the angle between the r and dl, that is nothing but phi. That is why we have written here sine phi. That is, this can be written as magnitude of dl is dl, the magnitude of this unit vector is 1, and this is dl sine phi. I write this as a dl sine 90 plus theta. Okay, I will tell you how I can write this as this phi as a 90 plus theta. For this, you consider this picture. This I redraw this segment here. That is, here we have of the distance vector, the distance s, and the length element makes an angle phi. Is okay. This is similar to this one, and this angle, this is according to this picture, that is theta. Fine. This angle is 90, and I write this as an angle x. If you concentrate here, this region, that is, this is this angle, this is a x plus phi, this is 180 degree. Okay, that is, here I can write the x plus phi is equal to 180 degree. Fine. Then what is this x? Okay, I will do one more steps here. This angle theta plus angle 90 plus angle x, that is the total angle of a triangle, that is 180 degree. That is x plus 90 plus theta is equal to 180 degree. Then now our aim is to find out this x. This x is equal to 180 minus 90 minus theta. Then this is equal to 90 minus theta. This is the angle x. Okay, now let us again, we can go back to here. That is, this x can be written as 90 minus theta plus phi is equal to 180 degree. Okay, I have substituted the value of x here, and again I have written the steps here. Then here the angle phi is equal to 180 minus 90 plus theta. That is, this phi is 90 plus theta. This is our angle phi. That is, this angle phi is nothing but 90 plus theta. Now you see here this angle, that is, this angle is 90 plus theta. Fine. What I did is, if you check here, we have written this angle phi is 90 plus theta. This 90 plus theta That is, you apply sine A plus B. That is sine A cos theta plus cos A sine theta. This is goes to 0. This is goes to 1. Therefore, the result is cos theta. That is, this dl cross r can be written as dl cos theta. Now, if you put this value, that is dl cross r is equal to dl cos theta, into this expression, and we can write our dB, that is, this can be written as, this is equal to mu 0 I by 4 pi dl cos theta divided by r square. Let me put this is equation number 1, or I will copy the same expression to the down. That is, B is equal to mu 0 I by 4 pi integration line integral dl cos theta divided by r square. This is equation number 1. Here I will do the little more algebra, and also I will find substitution for this dl. If you refer the figure, that is this figure, then it is clear that if you take cos theta, this cos theta is equal to, that is cos of this angle theta, adjacent side by hypotenuse, s by r. And also if you take tan theta, this length element will come into the picture. If you take the tan theta, that is, I will write this length element L here, and the tan theta is equal to opposite side by adjacent side, that is L by S, or I can write L is equal to S tan theta. Then if I take dl, because dl was our requirement, that dl is equal to, if I differentiate this with respect to theta, then this will be S sec square theta. Okay. Oh, and also from this expression, that is r can be written as r is equal to S by cos theta. I put this is equation number 2 and this is equation number 3. Fine. Then we need all those two equations here to replace this dl and to replace this r square. That is, this b can be written as mu 0 I by 4 pi line integral. Instead of dl, we will substitute that this one, L sec square, L is equal to S c square theta, is S sec square theta into here cos theta divided by, instead of this r square, we will substitute this one, that is r is equal to S by cos theta. Then r square means this is S square divided by cos square theta. Fine. This is equal to mu 0 I by 4 pi line integral. Okay, here we have to be very careful. We are changing the line integral into the angle theta. Therefore, this should be, that is, I bring your attention to this picture. That is, just now this expression dB, that was the magnetic field at this point P due to the small length element dl, and for which the angle was this one, that varies from this S to this R, this our theta. And if I consider another portion of the wire, that is here, then the magnetic field due to this small length element at this point P, for this we have to draw a distance like this one, and if this is the case, then this will be the angle that is varies from the distance s to this separation vector, distance vector r. Therefore, I make this is as a theta 2 and this is as a theta 1. If I add all such a kind of small length element dl on both sides of this wire, that is, one side it varies from, it goes from 0 to theta 2, another one is from this 0 to theta 1, we can say the total magnetic field at the point P due to this whole length of the wire, that can be obtained if you integrate this dB from theta 1 to theta 2, that is theta integral theta 1 to theta 2 dB. Fine. Now let us come back to this expression. Here, this expression, this should be theta 1, and the upper limit is theta 2. Then you can cover the whole length of the wire. Therefore, here the line integral, this should be theta 1 to theta 2, and here the 1 by cos square, that you can write sec square theta into s. In the numerator, here also you have s, here you have s square, and the numerator you have s sec square theta into cos theta d theta, because here the dl is, we have an d theta also. Okay, fine. It is very clear. This is c square and c square cancelled. This one s and this s cancelled. The remaining term that you have is B.Sc is equal to mu 0 I by 4 pi integration from theta 1 to theta 2. We are left with cos theta d theta. In numerator we have one s. What is this s? This s is the distance from the current carrying wire, that is, at a distance s we are finding out the magnetic field P due to this whole length of the wire. The s is the distance, that distance s is a constant. Therefore, this magnetic field B can be written as mu 0 I by 4 pi s integration theta 1 to theta 2, the integration cos theta d theta. This is equal to mu 0 I by 4 pi s. The integration of cos theta is sin theta, lower limit theta 1, upper limit theta 2. Now the situation is quite easier. We get the final answer, that is B.Sc is equal to mu 0 I by 4 pi s sin theta 2 minus sin theta 1. This is the final expression for the magnetic field due to the whole length of the wire at a distance s from the wire. That is, if I draw the picture here, that is, if this is a current carrying wire, then the magnetic field at a distance s from the whole current carrying wire, that can be found out using this expression, where theta 1 and theta 2 are like this one. From the one end, this varies from here to here, that is our theta 2, and the another length element, the theta 1, that is varies from here to here, this is our theta 1. Okay, the current flowing through the wire is I. Then this expression gives a magnitude of the magnetic field a distance s from the wire. What will be the situation? That is, we consider the case of an very lengthy wire. Very lengthy means an infinite wire. In the case of an infinite wire, infinite wire means a wire having the largest length, that is lengthy wire. If this is an infinite wire, we need to find out the magnetic field at a distance s from this wire. Then our expression we have is B.Sc is equal to mu 0 I by 4 pi s sine theta 2 minus sine theta 1. That is, the theta 1 and theta 2, if you refer this figure, theta 2 this way, theta 1 values to the left side. And in this particular case, if the wire is going up to the infinity, then this distance from that end of the wire, that is this distance that approaches approximately, that is this is nothing but the theta 2. This theta 2 approaches 90 degree. Clearly, from, if this wire is an infinite length wire, then from this end, if you draw a distance vector or the distance, the angle here that will also comes approximately 90. That is, this is the theta 1, that is 90. But this theta 1 is a minus 90 degree, because this is towards this left of this direction. Theta 2 is plus 90, because that is to the anti-clockwise direction. This is a clockwise direction. Fine. Therefore, this is a minus theta 1. Then if you substitute this theta 1 and theta 2 here, this expression, the magnetic field due to an infinite wire, current carrying wire, is given by mu 0 I by 4 pi s into sine theta 2 is sine 90 minus theta 1 is sine of minus 90 degree. The sine of minus 90 degree is nothing but minus sine 90. That is this minus and minus become plus. This will be the sine 90 plus sine 90. Then the sine 90 is nothing but 1. It is the magnetic field B can be written as mu 0 I by 4 pi s into 1 plus 1. That is mu 0 I into 2 by 4 pi s. This 4 and 2 cancel. The final expression for the magnetic field that can be obtained in the case of an infinitely long wire is mu 0 I by 2 pi s. Okay. This is one of the application of the Biot-Savart law. The same, that is the magnetic field due to an infinitely long wire, you can also find out using the Ampere's circuital theorem or the Ampere's circuital law. That is the distance s. You might have studied in the +2 class that the magnetic field, because of the current through this wire I, the distance s is given by mu 0 I by 2 pi s. Both expressions are the same. Okay, this is from the Ampere's circuital theorem. Simply we can say from Ampere's law. This is from the Biot-Savart law. Then this expression is quite important. That is, this expression is very important. You have to remember for the competitive examination. Okay, thank you very much.